So my name is Francisco Falcone. I'm at the Public University of Navarra. And first of all, I would like to thank Professor Saidi and the organization of MMS for the opportunity of talking with you of some of the concepts and some of the work that we are doing in relation to trying to analyze context-aware scenarios, specifically in the wireless system characterization of these context-aware scenarios. So there's going to be basically a brief introduction in the context. We're going to see a little bit some of the fundamentals of 4G, 5G systems, specifically on the 5G side. And then I'm going to talk to you about some of the work that we're doing in context-aware scenarios and where we can place sensors. And as you're going to see, sensors can be placed in very different and very exotic places, by the way. So to start with the introduction, some of you saw this slide yesterday, sorry for that. Well, what is the motivation for all of this? Well, the main motivation is that, as you know, there is an increasing interest in achieving the so-called paradigm of a context-aware environment or a smart city. Now, this is not just some sort of trend, it's not just some sort of, just way to do some sort of research. It's really necessary to do this because we are really having and we're really facing as populations some very interesting challenges in terms of sustainability, in terms of quality of living, in terms of government and democracy as well. So in order to achieve better levels of sustainability, we must, for example, interact with all of the energy systems. We're not only talking about energy generation, we're talking about distribution, we're talking about lighting systems, we're talking about waste management, we're talking about urban transportation, we're talking about the way in which we interact with our government or the way we interact with our peers. So basically what we want to do is that we want to have an environment that is going to be much more intelligent, it's going to have real-time feedback, it's going to be interacting with us. And wireless systems play a key role here because they're ubiquitous, they allow us to have high levels of mobility, and they're extremely scalable. So we're going to have to make use of them. Is that the only element we're going to use? No. We're going to have to use very powerful data networks that are going to be probably active optical networks. We're also going to have a very, very important thing to do in the way we analyze this data, and this is the so-called, trend and challenge of big data analytics and big data computation. No? So these are all things that are going to be in this scope of what we have to do. Now, I'm going to be very brief about this, that wireless systems have become extremely popular, and, nowadays they are very easy to access. This was not the case maybe 30 years ago, but for sure it is the case today. Now, it's not only a question about what technologically has changed, it's also a question about what socially has changed. And by using wireless systems, we are capable of doing things that we were not capable of doing previously. For example, having the possibility of working remotely or working on mobility, or the possibility of having certain type of interaction with administration that previously was impossible to have. Now, there has been a great increase in the number of terminals and services because there has been a strong decrease in the prices, not only on the hardware side, but very, very especially in the software side as well. And this was actually one of the main issues and one of the main concerns when GSM moved towards UMTS. They wanted a scalable, flexible, open architecture to do this, and this was really achieved. And also, there has been a lot of progress in the way in which devices have been developed. Please think of a telephone 15 years ago. Please think of a telephone now. A 3-year-old child manages an iPhone without any problem. And this is very symptomatic on the way in which applications have become plug and play, have become user-friendly for all of us. Now, there's another very important aspect. And it's the thing is that we are moving towards context-aware environments where we're going to have many sensors. And this has been a driver for Internet of Things and has been a driver, therefore, a myriad of sensors that can be implemented inside the structure of a city. Now, you can see many, many reports stating what is going to be the evolution of business of Internet of Things. The initial figures say that by year 2020, we are going to have a scalability that is going to be in the order of 50 billion sensors to 500 billion sensors that can be connected. The figures, as you can see, there's really 1 decade of difference. But in any case, even if we go to the lower side, which is 50 billion sensors, that means that we are going to have 10 times more devices connected to the internet than what we have at this point of time. And of course, scalability can be much larger depending on the things that we do. So therefore, in terms of wireless systems, we need higher bandwidth, we need higher capacity, we need higher quality in all of these systems. Now, just so you can see what has been going on previously to the advent of this type of context. Well, it is very interesting to note what is happening in the mobile business. In the mobile business, there has been a huge trend in which voice traffic has been really migrating towards data traffic in terms of the revenue of the operators. And the increase in the demand of data has been huge. Now, please remember what it was to transmit data on GSM, where we had 9.6 kilobits per second. What was the paradigm now, which is LTE, in which in a, let's say, a high mobility environment, we can reach values in the radio interface in the order of 40, 50, up to 100 megabits per second. So what is happening is that we're trying to achieve values of data capacity that we had over conventional ADSL lines or conventional, let's say, modem lines. We're trying to migrate that to the mobile case. The future is going to be, we're going to try to migrate fiber to the home up to wireless links. And this is really going to be the big challenge for 4G and especially for 5G. So the user case has been increasing. There's a user base that is increasing in a very, very steady way. And what is going to happen is that in a few years, we're really going to achieve a saturation level in terms of the number of terminals that we're going to have connected to the network. Actually, if we go to certain cases, there are already countries in the world where there are more mobile subscription lines than inhabitants. That's the case of Spain, for example, where there's 47 million inhabitants and there's more than 55 million subscriber lines. So penetration is huge. It's a huge business that is being developed there. Now, we also must take into account that in the same way that this business is evolving, the capacity of the networks is also evolving. And as we will see in a little while, capacity in the last 10 years has increased in the order of 1,000. And this is probably the figure that has to be increased in the next decade. And if you come to think of it, that is a very, very, very big number that we must achieve. Now, if we come to say what is going to be the growth that we're going to have in the systems, as you can see here, we are showing what is going to be the growth in terms of the traffic. Well, as you can see, the relative growth is going to be very, very, very high. This is a data from Nokia. And as you can see, the relative growth is in the terms of many, many times. And basically, we might experience a traffic 1,000 times increase. Therefore, we need systems that are capable of trying to support that type of traffic. Just one more concept. It's not only about the networks, it's about the way applications are interacting with us as well. Now, I don't know if you know these two applications. They're just two examples I wanted to share with you. One of them, as you can see, is called Google Now. Maybe some of you are users of Google Now. Google Now is a very interesting application which, taking into account the user state, and the user state is provided by the time zone where you are, it's provided by your habits, it's provided by your profile preferences. Well, when you do that, the application is capable of letting you know that you will be taking an airplane 10 hours from now, and it's going to provide you the best route, traffic route to arrive there. And it's also going to tell you, for example, what is the weather in your destination, so you can take choices when preparing your luggage, okay? This is not science fiction. This is completely real, and it's being used right now. And it's a little bit limited because there's one thing it still can't do, which is trying to predict human emotions. Now, the other thing that you have there, which is an application developed in Cambridge, it's called Emotion Sense. It's an application that is initially based only on software. And what it does is, by responding to a questionnaire in your mobile terminal, it's going to try to estimate what is your mood. What is your emotional state, right? And by determining that emotional state, it will, for example, try to provide you recommendations on what are the activities you should be doing in the day. Now, initially, it's only based on a questionnaire. It's a psychological questionnaire, but these people are already working on using the sensors embedded in your telephone to try to estimate, for example, your movement rhythms, or novel sensors which are still not embedded in the telephone, for example, trying to detect humidity, temperature, for example, to see if you're sweating, if you're not sweating. Okay, now this is a bit frightening, I know, but this is where we're going, okay? So we're going to devices and contexts in which they will sense how we are and will take decisions on the basis of what is our mood, if we're sad, if we're happy, etc., etc. Interesting. Now, there is no way you can achieve this. There is no way you can achieve this without using wireless systems. Now, let me be very brief because I have little time and I have many, many slides. Okay. If we go to the evolution of wireless systems, of course, we had initially public LAN mobile network. First system was analog system in the 80s. Basically, it was derived by the need of trying to provide access to the telephone system where you could really not put copper lines. And we have, for example, NMT in the case of Europe, TAX in the case of the United States. And there were analog systems. They were working in low frequency bands, wide coverage, 450 megahertz, 900 megahertz. We got a second generation system, fully digital end-to-end, and it's very powerfully based on signaling system number 7. Again, digital end-to-end, but it was basically a circuit switch system. Now, this provided very, very limited capability because you needed a modem for data. So 3G arrives, and 3G is, again, digital end-to-end, but it's a multi-service platform which has a core network in which you can have circuit switch and packet switch. Now, that's good because it can provide us with data transmission. Data transmission went up to 2 megabits per second in time division duplex. Time division duplex has not been really developed in any place in the world. Basically, everything has been frequency division duplex. So that gave rise to a new need. We need to increase capacity. And this was done, and virtually all your terminals are working that way, with high-speed packet access systems. Now, HSPA is really an evolution on top of 3GPP UMTS, which basically modifies the radial link, providing modulation schemes which are of higher level. For example, 16 QAM instead of binary phase shift keying or quaternary phase shift keying. But it also provides some evolution in the network because it's going to have data frames which are going to be smaller in terms of time length, and therefore it's going to be a faster system. And actually right now you can achieve on HSPA speeds in the order of 14 megabits per second downlink, 7 megabits per second uplink, which is reasonably good. Still, that's not good enough. And you know, 3GPP is really an organization which is focused in the way in which operators can exploit their networks. And you know, operators are businesses and they want to keep with the business. And that's why they envisage what can we do to keep on competing. So the 4th generation has evolved and exists today, and it's called LTE. And you know, I don't know if you know what the acronym means, but it means long-term evolution. This means what must we do as operators to keep our business in the long term? Yeah. So basically, we'll talk a little bit about what is being done there. But even when long-term evolution, which is really standard, release number 8, 9, 10, 11 from 3GPP has already been thought out and has already been established, even when it was being established, operators saw that it was not enough to cope with future data demands. And this is where 5th generation systems are being envisaged at this point of time. Now, as we will see, 5G systems are really an evolution of Wi-Fi systems. It's really a standard within 802.11, and more specifically, it's 802.11 AC and 802.11 AD. One in the 5 gigahertz band, the other one in the 60 gigahertz band. So basically, this is a very, very nice paper in the Communications magazine. I really recommend you to read it. It's not from me, a shame. And it really gives a very, very good insight on what has happened up to now and what is envisaged that can happen in the near future. Now, what has happened in the last decade is that basically there has been an increase in capacity that has been 1,000-fold. Now, if you think of it, 1,000 times is a lot. It's a huge, huge number. Well, this has been true, and this has been achieved. Please think of 9.6 kilobits per second, and nowadays there's no problem. You have 10 megabits per second. No problem with that. But 10 years ago, believe me, I worked in an operator. No one thought we would be going at 10 megabits per second. Now, what we're saying now is that, okay, what we need as the next wave is to achieve 1,000 times, again, capacity increase. So think of it, wireless links that can be going at speeds that are multi-gigabit per second. And not only as fixed point-to-point links, because this is achievable nowadays via microwaves, via millimeter waves, even via terahertz systems and infrared systems. No, we're talking about mobility. We're talking about microcells, femtocells, picocells, which can operate with an antenna, which is not a directional antenna, and which is providing very high speed to the user. So there's many things that can be done there. The basic thing that was done previously was to increase radio spectrum efficiency by increasing basically modulation scheme usage. Now, for example, LTE is already starting to use very high level modulation schemes. Okay, 64 QAM is something that is normal in LTE. And we will see that 5G systems is trying to envisage 256 QAM. But if you guys are working on digital systems, you do know that probability of error is strongly dependent on the constellation. It depends on the EB to N0 ratio. And as the constellation starts to get more complex, there is a very strong limit on the space you have in the signal space in order to have any type of error. So you really are bounded there. So can we go, for example, to 512 QAM? Is that possible? Well, it seems to be a limit that is going to be very tough to break. So other things have to happen, as we will see. Now, if we go to 4G, I'll try to be as quick as possible. Now, LTE is long-term evolution. It's the release 8 of 3GPP. It's a full IP network. Important, it's full IP. There is no circuit switch in LTE. All the network, the complete network is IP, end-to-end. Now, we have we have circuit switch emulation, right? By the call control function server, which is the one that is going to be basically controlling delay in the network, okay? There are very important features. We have multi-spectral content, okay? Now, this means that we can have several types of spectrum blocks. We have initial blocks that can go from 20 megahertz up to aggregation of 100 megahertz. And this is what we need, for example, in LTE Advanced in order to have 1 gigabit per second maximum capacity of LTE. We have high-level coding and modulation schemes, of course. We need them in order to get these speeds. We have very small latency. And we have very small latency because we have a lot of the network intelligence in the nodes. They're not in the network. They're in the femtocells, in the microcells. This did not happen in UMTS. It started happening in HSPA, as we will see, but it does not happen in UMTS. Of course, there's already the possibility of using MIMO. This is a very keen community to antennas, so MIMO is a very attractive thing. Let me tell you that MIMO is not as nice as it seems. MIMO is complex, and operators are not thinking of using MIMO in LTE. They're thinking of using, in any case, MISO systems, because just do a simple exercise. How can we put in a conventional terminal multiple antennas to have the MIMO system? It is very difficult to do. And if you talk to Telefonica, for example, or to Vodafone or whoever, they're going to tell you, no, we don't want MIMO antennas. We don't want that for anything. Whoa, but the antenna community is analyzing all over the place MIMO. Why? Because MIMO is very useful in 5G systems, not really in 4G systems, okay? Right? I know this might not sound very good to some people, but that's what there is. Now, of course, it's also very important. We are using also other techniques such as OFDM. Again, OFDM only in downlink because it's very, very power demanding. And we're using single carrier and uplink for now. Now, taking this into account, network architecture. The network architecture of UMTS is LTE is very simple. We are going to have terminals connected to E-node Bs, enhanced node Bs. We're going to have the MME. The MME is going to be the mobility management entity. It's going to establish the connections to the core network. Now, All of this is going to be IP connections, everything. And voice is going to be a voice emulation. It's not going to be circuit switch. Now, very important, as you can see, there's some interfaces which are going to be connecting in the user plane as well as the control plane. You see here a new interface that did not exist in UMTS. It's called an X2 interface. This is going to enable the possibility of interchanging information in the radio interfaces in order to have a very interesting feature that's called self-optimizing networks, okay? The protocol stack that we're going to have in the terminals is this one. This is going to be in the eNode B. There's a huge amount of intelligence in the eNode B. What happens when you have a huge amount of intelligence in the eNode B? Your latency drops dramatically because you don't have to connect to the core network. Almost everything on the radio resource management is going to be done locally. And this is very, very important. And this is a paradigm that we're going to use also in 5G systems. Now, just to show you that there's a huge amount of things on LTE. LTE is not that novel anymore, okay? LTE Advanced still is cool. LTE is the normal thing. And please take a look at this. The important thing is not the terminals. Terminals is fine. This is an LTE femtocell. Now, I'm sure that many of you at your home have a router, right? You have your Wi-Fi router, right? And it's connected to the network. Now, operators in the future are going to sell you that, not a conventional router. And what is going to happen is that you're going to have multi-system connectivity, which is going to be seamless, and it's going to be plug and play. Your telephone is going to connect to the best network. You might think that you're talking via, for example, a conventional UMTS network. No, you're connected and you're talking voice over, for example, LTE, okay? Or Wi-Fi, it will depend. This is nice, isn't it? This is the network. Interesting, simple, huh? Now, one thing that I wanted to show you about the network. I know this is small, okay? But I don't know if you can see that here it says 2G. 2G, right? And here you can see 4G. And you have anchors, they're called anchors, to go to 5G. Every single thing is connectable. Every single thing is connectable. So you can have a terminal where you can start a conversation in a GSM network because it has umbrella coverage and it covers everything, and you end up talking with LTE. There's no problem. There's something in there that is going to control it. I'm not going to talk about the core network. It's very fun. I'm not going to talk about that today, okay? There's no wireless systems there, almost anything. Where are all the wireless systems? All the wireless systems are in the border of this image that you have here. So, when we go to this, prior to talking about 5G, we must talk about WLAN. Now, very simple. WLAN is the way in which Ethernet was provided wirelessly. It became very popular when Intel started introducing all this functionality in the chipsets, and this is why it became so popular. And it has many features. It supports different type of modes, infrastructure mode, ad hoc mode. It supports different implementations of the physical layer. This is what gives rise to the different letters you have in Wi-Fi, right? 802.11a, b, g, n. Well, it's basically modifications in the physical layer, not only in the physical layer, because, for example, you have 802.11e, which is a security mechanism, or AA, which is really quality provisioning, for example, but it's basically that. And Wi-Fi has been really implemented for a lot of things. Very important, these different letters give us different capacity. So basically, 802.11 initially was 2 megabits per second. Evolution towards B is 11 megabits per second. AG is up to 54 megabits per second. The more trendy right now is 11N, 600 megabits per second. This is given due to the fact that we use MIMO. And what is 5G? 5G is this and that, which is basically 802.11ac, 802.11ad in the case of millimeter wave systems. And basically, what is going to happen is that we're going to introduce high-level capacity systems there. We're going to introduce, for example, very powerful MIMO mechanisms, 8x8 MIMO, for example, which you can understand that it's very, very complex. And we're also going to try to reduce latency as much as possible as well. So, basically, 802.11ac is just an amendment, okay? And the amendment of N is trying to increase system capacity. It's going to be evolutionary. It's going to try to work well with other Wi-Fis because there's a lot of Wi-Fi deployed. Now, we're going to use multiple streams, and very importantly, we're going to use very cool types of MIMO. not only bidimensional MIMO, conventional beam steering, we're going to use three-dimensional MIMO, okay? Which is very cool. It's very interesting, especially for all these students that are doing antenna arrays. Yes, we got to do antenna arrays, and they have to be beam steerable, and they have to be very nice to work, and they have to have very little side lobes, by the way, because if not, we're going to interfere the whole thing. Also, very important, we're going to use channels that are going to be wider. Actually, the minimal channel that we will be using uses channel aggregation of 80 megahertz. It's a very wide bandwidth channel. So when you design the filters, again, let's have a good quality factor, but not that good. We need enough channel bandwidth in order to work there. Of course, there's other things like intelligence management of interference, smart antennas, beamforming, and of course, it has to be energy efficient. Now, what is the expected maximum capacity up to now by the standard? 6.93 gigabits per second using 8 streams of MIMO in receiver and transmitter. That is radio interface speed. That is not application speed. That's the bits you would measure if you could measure them in the radio interface. Of course, you have coding, and of course, you have other elements that are going to reduce the overall capacity that you have in your system. Very important thing, I'll try to be fast, is the fact that the network architecture is going to change. This is the picture that we would have of LTE now. Macro cells that are going to be providing services to smaller cells, and in some cases we're going to have Wi-Fi offload in order to reduce the capacity demands that we have on the network. What is going to be the evolution in 5G? There's a very important thing you must take into account. If we reduce interference, we increase capacity. We dramatically increase capacity. So therefore, we must put our antennas as close as possible to our traffic sources. And we must minimize interference. So one of the things that we want to do is we want to have very small cells. They're not even called pico cells, they're atto cells. They're very small. They're very high capacity, but they're very small. So if we want small cells of high capacity, we need to put a lot of small cells to work together. And this is going to give rise to concepts such as device-to-device networks, which are going to be interconnecting machines in the case of Internet of Things, and also a very interesting concept which is called cloud radio access networks. What does that mean? The radio resources are managed in an intelligent way by an entity which is controlling all of the interference of a certain region of the network. This is going to optimize the capacity because it's going to reduce the interference. Here we have some results where we can see how this capacity is changing. I have a strong limitation in time, so I'll be very quick. Another thing, latency. Latency is another vital point which I wanted to talk about. Now, basically the latencies in which we are working now as mobile network are here at 100 milliseconds. There has been a lot of research on what would be really the extreme context-aware interaction environment that we want. Well, the extreme case is the case in which you have the same time response as in a tactile system. When your body touches something, the time your brain understands that it has touched something. Well, this time is approximately 1 millisecond. So if we want to achieve the most, let's say, context-aware environment that is really sensing and is really trying to adapt to you, then we go to what's called tactile internet immersive control, where the network is going to respond in 1 millisecond time. Now, if any of you have done pings on a network, I dare you to get 1 millisecond response time. It's going to be a huge challenge. What has to be done in order to get that? Very small networks and a lot of intelligence locally in order to achieve this. Of course, the architecture, there has been quite a few talks today talking about the transceivers and talking about the fact that they have to be scalable and that we're going to have tunable systems, obviously, of course. So I'll be fast on that as well. Just a simple thing. I said previously that MIMO does not go in telephones. I stick to that. There has been work done on that. Of course, you can put MIMO in a telephone if it works in the millimeter wave band, okay? And that's the case, all right? So if any one of you tries to send a paper to IEEE saying you've done a terminal that is UMTS and it's working at 2 gigahertz or LTE and it's MIMO, well, I think you're not going to be successful. That's my opinion, okay? Well, just one thing. What do we want to connect to this 5G system? Wireless sensor networks, okay? And wireless sensor networks are going to be basically driven by Bluetooth, Zigbee, ultra-wideband, and some other very cool systems. For example, 6LoWPAN, which is full IP, or N-Ocean, which is energy harvesting-based systems, okay? Now, they're going to be basically defined, but what is the way in which nodes interact? What is the topology? What is the consumption? That has to be very low, basically. The unit cost has to be very small as well. It's going to have low bit rate. We really don't need to have high bit rate. And very important as well, we're going to have specific operating systems that are going to be very, very efficient in terms of lines of code. For example, TinyOS. It's a very small system. You need a very small microcontroller with, for example, 8 kilobits memory range, right? So basically, we're going to apply this in many, many places: smart homes, building automation, etc. Here you have some of the examples. This is an ocean. I don't know if any of you know it. Very interesting. Please go to their webpage. And here you have some of the calculations and some of the estimations we do in our group. Again, coverage, capacity. It's not about putting antennas so you get signal level. It's about the signal to noise ratios you have. And indoor environments are very complex, okay? And here what you have, for example, is the signal to noise ratio inside a conventional scenario like this one. And as you can see, it's topologically dependent. And it's not a linear relation. It's really going to depend on all of the complex issues you have inside a building. Actually, if you do that, you then have to do radio planning and saying, if I have thresholds in what is going to be the sensitivity of my transmitters, what is the amount of transmitters I have to put in? What is the best optimal location in order to place them? Not only that, depending on your network configuration, you can do the estimation of what is going to be the power consumption you're going to have of your transceivers topologically in the scenario. You can't place antennas anywhere you want. You have to place them in the optimal location where energy consumption is going to be reduced. Just a very simple comment: interference. Interference can arrive from very, very special places. That's a microwave oven there, okay? And you're going to say, why are you talking about a microwave oven here? Well, we had a colleague in New Zealand that was doing a smart home, and every time that he wanted to heat his milk and his coffee, all of the wireless sensor networks inside his home stopped functioning. And he said, well, couldn't that be leakage from the microwave oven? Well, probably it could be. So for example, a novel model was developed in our case. It's an antenna array model based in order to try to derive what is happening inside in a scenario. And this is basically the way in which radiation is produced in the scenario in which the microwave oven was operating. Now, this is the measurement of the spectra of the microwave oven. This is a Zigbee channel, and this is the microwave oven. Now, I'm sure that you can see graphically the signal to noise ratio if I move the channel, right? And if I get inside here, what is going to happen is that the packet error rate is going to increase dramatically. So, of course, we have interference sources, many, many interference sources that can really degrade our system. Now, going back to context-aware scenarios, I'm going to be very fast on this. We really can use 4G and 5G systems as the backhaul of this. And what examples can we use? For example, this is a street lighting system we have been working on. It's interconnected by Zigbee sensors, and it's going to use a fuzzy logic in order to try to estimate what is the lighting that we need in every single point of time. Now, this is the system. Here you can see the coverage propagation that has been calculated using deterministic codes, and this system was implemented. Why do you have to do this? Because if you have a lighting system that is old, you cannot interchange everything. You need to adapt this old lighting system. You can also have VANET. I talked a little bit about this yesterday. You want to interconnect vehicles because you want to provide messages for the users, for example. And there you can have different effects, for example, Doppler shifts. This, for example, is the measured Doppler shift for an 802.11p system, which is a high mobility system. And you have to take this into account when you design, for example, your context-aware environment with cars. This is the real system, very cool, whole bunch of antennas, magnetized, very nice. When you go to the street, they look at you, of course. This is a train. Again, we want to have a context-aware environment, so this is a real train system in Spain. CAF built this train, and we provided sensors inside of the train to see how this was working, for example. These are some of the results, measurements, power, packet error ratios, etc. This is radio channel configuration inside of a bus. And again, we want to provide sensors inside the bus. Why we want to provide sensors? Because in this case, the municipal company of buses in our city had a very simple problem. We want to count the number of people that go inside the bus and go outside the bus in order to do traffic routing. And you can say, it's simple. You just put the ticket and see how many people go in. Yeah, that's simple. It's not so simple to calculate how many people go down. So they wanted a wireless system in order to do this, which would be context aware. It would be connecting with the network, okay? Here you have some results. An airplane, I talked to you about this yesterday. We want full connectivity. In the future, connectivity will be provided in an airplane. If you go in a continental flight in the US today, you have Wi-Fi access in some planes. This is not a very novel thing. And you know that there's also law changes in order to try to have full connectivity of mobile phones in an airplane. If you are used to going in an airplane and all the phones are off and that's so nice, well, that someday is going to stop because the phones will be allowed to function. And actually, the standard does support mobile base stations inside an airplane, okay? So just take that into account. This is for home automation, again, trying to analyze what is going to be the context-aware environment for a domotic system, building automation, smart automation systems, and so on. Judo, whoa, what's that about? Okay, so this is a very simple system. We only connect Zigbee sensors on a judoka, right? The idea is not to do this. The idea is to embed textile antennas inside of this. But as you can see, again, we are trying to have a scenario where there was no connectivity and it has become suddenly a context-aware scenario. The idea, this is very interesting for the Federation, is to provide immediate access, for example, via gyroscopes or magnetometers of what is the position, the location of the judoka, because, for example, there are some illegal positions, or because you want it for training, or you want it for biomedical purposes, for example. This was very fun to do, by the way. And here you have the application. There's actually a video we have on YouTube of the system working and how you hit someone and all the sensors go up and down. Really nice. Surfboards. Now, we had a very, very fatal accident recently in Spain where 2 surfers died, and it would be very interesting to have interconnectivity of a surfboard, for example, 2 embedded sensors inside of the suit and also 2 gateways that would be outside. And so we provided the simulation, and this would be the simulation of the sensors. This would be the equivalent of the surfboard. This would be the equivalent of the surfer and a buoy, and therefore we could analyze an ad hoc network. Context-aware environment in the sea. There would be no problem to do that either. E-health, we have also a development in which a Holting, which is basically an automated electrocardiograph system, connects via Bluetooth gateway and therefore provides all this information to the hospital. Well, of course, you need sensors to do this, and we provide all of the simulation scenarios, techniques, and so on and so forth. And this is just another thing. Smart city context, we're trying now to go to a full wave simulation techniques that have to be optimized in order to put really big items. This has all been done in-house in order to really get big scenarios. Yeah. Oh, I know. Yeah, I have just 1 minute. Yeah. This is only another example in a smart city context urban. This is trees, sensors in trees so they can locate you, okay? Just ask me later if you want. Those are the trees, sensors, people, trees, okay? And this is the last thing. We're also working on a very interesting concept which is called the smart health paradigm, in which you interconnect all of the systems in order to have the best possible health provisioning. For example, imagine you're allergic to something. You would have connectivity to tell you what is the best route you should take in every single day in the city in order to try to have the least possible contamination because you have a treatment for your lungs, for example, okay? So basically, bottom line, we have many applications in which you can embed and you need a wireless transport network, which is going to be a backhaul or can be the access network, in which 4G and 5G systems, due to their bandwidth, is going to be very, very interesting option. There's a lot of issues there. There's a lot of work to do because they're very sensitive to interference, very, very sensitive to interference. So it's cool to do antennas that are going to be beam steerable. It's cool to do filters that are going to have very good quality factors. And all of that is, I hope, is going to be a good impulse for all of you to work. It's a very, very exciting challenge. So sorry for the time, and thank you so much. And I'll have any questions. Thank you.